The final exam for semester 2 will be 25% of questions from semester 1 and 75% from semester 2. So let's get started with semester 1 stuff, and specifically this video is going to be about some of the Unit 0 concepts. One of the concepts that we learned about was called specific heat. Specific heat is how much energy it takes to heat up a particular substance by 1 degree Celsius and 1 gram of it. So, for example, pure water is one that we've talked about a lot. It takes 4.2 joules to heat up 1 gram by 1 degree Celsius. So if you wanted to heat up 2 grams of water by 1 degree Celsius, it would take 8.4 joules. Similarly, if you wanted to heat up 100 grams of water from 25 degrees Celsius up to 26 degrees Celsius, that's 100 times what this standard is, so it would take 420 joules for that water to heat up. So let's take a look at this specific question. It says the specific heat of ocean water is 3.99 joules per gram degrees Celsius. So it takes 3.99 joules to heat up 1 gram of ocean water by 1 degree Celsius. It's more difficult. It takes more energy to heat up pure water, 4.2 joules. So explain the difference between these two liquids. So we can say this in a couple different ways. Pure water requires more energy to heat 1 gram by 1 degree Celsius than an equal amount of ocean water. Let's take a look at a problem with some math in it. We learned about an equation, Q equals M times C times delta T, where Q is the thermal energy, and that's measured in joules. M is mass in grams. C is the specific heat, and as we can see from the last problem, this is how many joules it takes to heat up 1 gram, 1 degree Celsius. And the triangle T actually means the change in temperature, so the difference from where you're starting and to where you're going. So it says, what if we change the temperature of 95 grams of copper by 15 degrees, and that required 850 joules? Then what must be the specific heat of copper? So you could easily Google this, but let's figure out the experimental value. So I'm going to rewrite my equation, and I'm going to note that I know the mass, I know the change in temperature, and I know the thermal energy. So I'm missing C, the specific heat. So I'm going to solve the equation for C, which means I need to divide both sides by M delta T. So now C equals Q divided by M times delta T. Now I can plug my values in. 850 joules divided by 95 grams times 15 degrees Celsius. That comes out to be 0.596 joules per gram degrees Celsius. So that is my final answer. Number 3 is all about calorimetry, and I want to remind you that calorimetry is all about burning a substance like a fuel, or like we did in class as well, food, and you make the assumption that the thermal energy released by the substance is equal to the thermal energy gained or absorbed by the water. Now that's quite an assumption because this is not a closed system. As you can see, some of the thermal energy will be transferred to the surrounding air, to the material that the can is made out of, but it's pretty good. So let's take a look at the specific numbers. We know something about water. We know the specific heat of water, which it gives you. We know the mass of the water. And we know that while the butanol was burning underneath the can, the temperature changed. I'm going to calculate that temperature change by taking my final temperature and subtracting my initial temperature. That comes out to be 11.2 degrees Celsius. And so now I'm ready to actually calculate how much thermal energy was transferred to that water. So I'm going to take the mass of the water times the specific heat of water, the 4.2 joules per gram degrees Celsius, and multiply it by the change in temperature, 11.2 degrees Celsius. Now right away I can see some of my units are going to cancel out. Grams and degrees Celsius, I'm going to be left with joules, which is good because I want to know how much energy that butanol was giving to my water. So this comes out to be 65,856 joules. If I look back at the actual problem, it says it wants to know how many kilojoules of heat energy are produced per gram of butanol. So I've got to get this into kilojoules by dividing by 1,000. That comes out to be 65.856. I'm going to carry the decimals and round a little bit later. Now it says per gram of butanol. It's important to know during this process how much fuel was actually burned off. The more fuel that's burning, the more energy. So that's important in our calculation. So now I'm going to divide by the 13.7 grams of butanol, and this comes out to be 4.8 kilojoules per gram. That is how much energy my butanol is releasing to the water. So we make the assumption in the end that that is how much energy that the butanol contains. In this experiment, it says describe any transformations that are occurring and be sure to specify, and transfers, and specify the difference. Well, transformation is basically a conversion from one form of energy to another. We saw that the chemical potential energy of the fuel was transformed into thermal energy and radiation, the light from the flame. And then from there, we saw the thermal energy transferred to a few different places. We saw it transferred to the water. We saw it transferred to the air. We saw it transferred to the can. And to define a transfer, it's simply the movement of energy from one place to another. Point A to point B. And finally, it says we assume all the thermal energy is transferred to the water, but what is a major source of error in the experiment? Some thermal energy is transferred to the air, and therefore it's not accounted for because the butanol actually is giving off more kilojoules per gram than what we measured in the experiment, because some of that energy that went to the air should have really gone to the water.